Alrighty, so here we go. This is how to get a merit on the first practice roll experiment with the pendulum with this t equals 2 pi squared on L on G. So what we're aiming for is something like this, okay? So hopefully you've already got the achieved graph because we get to strap bits to it, like error bars. And we get to get the equation of the error line, and then we get to do some calculations based on those line equations, and then finally we get to add an extra bit into our conclusion to get a merit. So, how this looks. First off, let's just review the plan. You should already have an achieved graph, all right? Line of best fit, labels, zoomed in axis. So that should already be done. So the next thing to do is probably to think about some controlled variables and slap that information down above your data table. Then we get to think about, well, what should the gradient have been? So you use the equation and calculate the theoretical gradient. Then it gets a little bit crazy, so hang on. We get to calculate these things called error bars. Then we get to turn those error bars on, make sure they're working correctly. Then we get to draw the error line using about half of the error bars if we can, okay? Then we get some points for our error line, okay? The error line is always a bit tricky in a merit graph. Finally, we're going to have two equations and we do some calculations, and that'll tell us how good our line of best fit gradient is. And then we change our equation to include this uncertainty. And finally, we add a few sentences to our achieved conclusion so it can be worth merit. This is usually a 2-page printout out of Excel to get merit. So let's start playing. So the first thing, in this experiment, there's not that many controlled variables, let's be honest. All you have to do is keep the amplitude small. In most experiments, there will be obvious controlled variables. Other things in the equation, in this case it was just t equals 2 pi square root of L on G, saying G is a controlled variable is too stupid to even bother to mention. But in most experiments, there will be some type of control. The next thing you should probably do is go and track down what the theoretical gradient should be. In this case, with this graph, t on the vertical, square root of L on the horizontal, your gradient should have been about 2.006, which is a little higher than what we're getting. Here's our achieved graph. You should watch that other video if you don't know where this came from. So, error bars. Well, error bars. Error bars is a weird philosophical thing that basically bring in how good each dot is. The uncertainty on each dot will go left and right and up and down. Sometimes they're too small to even show up, but we have to calculate them. So on our horizontal, here we go, I'll put it here, okay? So error bar. For the horizontal, that's going to be how good each square root of L is, okay? Now each square root of L came from each L, funnily enough, and each L has a plus or minus of 0.003, which is 3 millimeters, estimating to the center of mass location. So we're going to use that 0.003, and we're going to divide by each L, then we're going to multiply by what we're graphing. And what we're graphing is the square root of L. And then we're going to multiply by the power of the thing we're graphing. So in this case, we're going to multiply by 1/2. So that's our formula. It's not really a formula, it's more notes. This is how we're going to do it. Okay, which is always good to type how you're going to do it. Here's how you type it in Excel. You have to use equals, otherwise Excel doesn't know you're trying to tell it to calculate anything. So equals 0.003 divided by, and you click on the first L. You multiply with the star above the 8. You click on the square root of L that pairs up with that L. Then you multiply the little star above the 8, 0.5. Okay? You enter, and that little tiny number is how good this 1.18 is. Okay, that's the uncertainty on that square root of L that came from the L of 1.25. That is the horizontal one. The vertical E-bar deals with, in this graph, how good each average period is, okay? And how we do that is we will always take the maximum number, we subtract the minimum number, you divide by 2, and in this case, we have to also divide by 5 because the times we took were for 5 periods. If it was just a bog standard average, without the 5 period issue, you could have just take your max minus min, divide by 2, and you're done. But in this case, we have to divide by 5 as well. Now, how you get Excel to do this is you said equals. This is a little bit tricky. You need a bracket. Then you say max. You need another bracket. And you drag across the 3 numbers, and it'll find the biggest number for you. Close that bracket. Minus. Min. Bracket. Drag across the same 3 numbers. Close that bracket and close the other bracket. So you've got 3 sets of brackets here. That's just found the smallest and the biggest number and subtracted them. Then we want to divide by 2 and divide by 5. Hit enter, and that tells us how good the 2.164 is. It's good to the nearest 0.02. So make sure you check each of these with a calculator so that you know Excel is doing what you think it's doing. Also, make sure you type in what you want Excel to be doing. So right above these 2 numbers, I've typed in the idea of how I'm finding these 2 numbers. Okay? You can drag that little thing all the way down, and it finds all the rest of them for you. So now we have these error bars. This tells us how good. So these tell us how good these are, and these tell us how good these are. Now we have to get these on this graph. So here we go. If you select the graph and you go to the plus symbol, we can turn on error bars. And when you do that, it just gives you the same error bar in every single dot, which is not really that helpful because we want the horizontal ones to be this column of numbers, left and right. We want the vertical ones to be this column of numbers, up and down, okay, plus and minus. So how we play that game is you select the horizontals. You can right-click and format the error bars. And down here, you customize the horizontal ones. You specify the value. And you click on this little thing here. And you want horizontal, so you want to select these numbers. Close that, and then you want to select the same exact numbers. Make sure you get the horizontal ones. And you hit OK. And now, if you notice, those horizontal error bars are pretty much too small to see, which happens, okay? But you have to go through the process to see if the horizontal error bars are big enough to matter. So for the vertical ones, now you have to customize those, okay? So you right-click on the vertical, you format the error bars, you scroll down to the bottom, you customize. You specify the value, you click on the positive one, and you want these numbers that you just calculated for your vertical error bar. Do it again for that bottom little business. So up and down. You finally click OK, and now we have error bars. They're not very big. They're not very big at all. But we have to go through this process to make sure that we can get a merit. So we're getting closer. We've got a few other things to deal with here. The next thing to deal with is maybe to zoom in the graph even further. You need a zoomed in graph to get a merit. So we might as well zoom in that axis even further on the horizontal axis. And we can zoom it in to 0.75. Because the closer you are, the better you can see these error bars and how to draw the second line on your graph. The second line on our graph, we're going to try to aim for 4 of these 8 error bars. There's 8 points on the graph. We want to use at least half. In this case, 4. If you don't have 5 dots on your graph, you're going to fail. So Make sure you have more than 5 dots on your graph, and then you're going to look about half these error bars. And I'm looking at the ones in the middle. The 3rd, 4th, 5th, and 6th dot. They can actually maybe line up with a ruler and make an error line that's steeper than our blue line of best fit. Okay? So, it's similar, if you watch the other video, let me get rid of that cheap little conclusion. It's similar to how we actually found, how we plotted the second line on the other graph. But here's what I'm going to do. I'm going to type this in below my data table. So this is error line. And this is going to be my horizontal values. And this is going to be my vertical values. And I'm even going to make a little note here that I'm going to aim for the 3rd. And technically, I'm going to aim for the bottom and the left, because what that means is on this little 3rd dot you can subtract down and subtract left. So that means equals, it's going to be that 3rd one, in this case is this number here. I'm going to subtract this error bar. So that's going to move it left. Remember, that's the horizontal. And then for the vertical, I'm going to select that 1.738. And I'm going to subtract the vertical error bar to pull it down. Because you probably wouldn't have had that there either. So then we want to say that's 1st, 2nd, 3rd, 4th, 5th, 6th dot. That's what I want, the 6th dot. And I'm going to aim for the top right. So what that means, equals 6th, 1, 2, 3, 4, 5. 6, the 1.02 is the one I'm hunting, and I want to go to the right, so I want to add this horizontal error bar to move to the right, just a little tiny bit, doesn't move much. And then I want this 2.02, and I want to add the error bar to move it even higher on my graph. So I've calculated these 2 points. Now, if you want to turn on a second set of points, remember, you right click, you select data, you add, you call it an E line, and you want to select your range like this, and then you want to select your other wide numbers like that, and that is how you get the 2 little red dots, okay? So now the game is joining the red dots with a trend line. You could do it just by right-clicking and adding a trend line. This time you will want the equation of your error line, okay? So you will want that equation. Now, if you look carefully, it's not really going through 4. It's a hit and miss kind of game with these error lines on a merit graph. That little one right there is below it, so you know what? I'm actually going to aim for the next one up. I'm not going to aim for the 6th, I'm going to aim for the 7th. So if I go back here and I just change a few things, and you aim for the 7th, and you just play around with it. So these, instead of using A20 and D20, which is A20 and D20, we can move it up one and go for A19 and D19. And if you watch, that little red dot just moved. I also have to move this one to use B19. It highlights the numbers, and E19. And now if you notice, the little red dot, the 2 little red dots, the line that's joining them is at least going through half of my error bars, okay? It's changed my equation so that now the gradient of that equation is durable. If you don't trust it, you can turn that off and you can turn it back on by just options. Oops, let's try again. Format that trend line, there it is. Always right click, format the trend line, display equation on the chart. So there it is again. So my error line is this one here. So you probably want to title it error line. We actually could have a capital E if you want. Now, Again, you need to get rid of that y, and you need to put a t on it, because on this graph, that's the vertical axis, and you need to get rid of the x, and you need to put an L to the power of 0.5, because that's for this. So we have two lines, two equations. They're crossing each other. The error line, in this case, is steeper. So, this is a merit level graph, okay? The next thing we do is we do a few calculations. So most people would probably insert a new text box. I'll do it up here so I can see everything. We can move it around later before we print. We want to get the uncertainty of the line of best fit gradient. And what that's going to be is the subtraction of the two gradients on our equation. Okay, so that's 2.204 minus 1.8972, and you get that subtraction 0.3068. And now with these, you want one significant figure as long as they're decimals. If it's bigger than 1, just round it off to the nearest whole number. But most of them will not be bigger than 1. What that means in this case is 0.3, so you round it off to 1 sig fig. Now this will change your final line of best fit equation. Okay, we're going to include how good the 1.8972 is with this subtraction we just found. It looks like this: t equals bracket 1.9 plus or minus 0.3 times the square root of L, and then you can add in your intercept of 0.06. Some people would even round it up to 0.1. So the logic of this: we've rounded our gradient to be the same number of decimal places as the uncertainty that we found by subtracting the two gradients. The intercept we have rounded to be the same number of decimal places as the gradient of 1.9. So it's a bit more honest than being as insanely specific as XL is with its numbers in the equation. The last thing you can do with this is we have calculated what the theoretical gradient should have been, 2.006. We can find the percent difference of our line of best fit gradient versus the Theo gradient. And how that works is you take your 2.006 expected, you subtract your 1.8972, some people use 1.9 instead, you divide by what it should have been, 2.006, you multiply by 100 to turn it into a percentage. So you want the difference of what it should have been versus your line of best fit, not your error line, your line of best fit. You get that difference, you subtract by what it should have, you subtract. You get that difference, you divide by what it should have been, and you multiply by 100 to make a percentage. To be pretty much 5%, okay? So, now we're ready for our conclusion. The conclusion will include these bits that we just found that you don't need to do for achieved. Whoops, my text box is a little too short. Let me stretch it down a bit. The merit conclusion. Okay, so how a conclusion looks. We're almost there. We're honest, I know it's a long run. Here we go. So the first two sentences are identical to the achieved, with the only difference being we have rounded off our gradient and we have included how good our gradient is. It's called uncertainty. And we've rounded off our vertical intercept. So the first sentence, that's all we changed. The second sentence is identical. You need the second sentence to pass because you have to say that your relationship matches the theoretical relationship. And almost always it's because that your relationship came from straight line dots. Here comes the merit part. Your gradient, or our gradient, of 1.9 plus or minus 0.3 has a range of 1.6 to 2.2. You get that by subtracting and adding the two numbers of 1.9 and 0.3, okay? Now this range of values for our line of best fit, in this case, includes the theoretical of 2. In fact, you could even say that my 1.9 gradient is only 5% off of the expected 2. This gives my results, which, for those of you who still haven't figured it out, your results are your graph, your equation, and your line of best fit. It gives these things high validity because this is exactly what you want to have happen. You want your range to be sort of smallish, but you want your range to include the theoretical value, and you want your percent difference to be pretty small. Okay? It doesn't always happen. If it doesn't happen, that doesn't mean you can't get a merit or excellence. That just means that you have other things to talk about later in your discussion. This is your merit, okay? It takes quite a bit more time, and it takes a little bit of know-how, knowing exactly what to do to calculate these error bars, how to turn these error bars on, how to scale those error bars so that you then can see where to put these error lines. And the error line, you have to then figure out which dots you want to use. Then you have to turn the error line equation on. Then you have to do some math. It's not much math once you know what to do. Subtracting two things, rounding some things off, and then subtracting what the theo was, dividing by the... So it's not much math. But that's the idea of a merit. Okay? Everything else will be in the discussion. We even, remember, had our controlled variables back up here. Okay? Hopefully this helps. You will need to practice this quite a few times so that it's just part of almost your muscle memory. So you know you can get a merit and you don't leave anything out. Good luck. Ask for help when you need. So the merit conclusion. What I might do now is start moving these around to fit onto my second page. My second page is past that dotted line, and we can make our graph a little bit shorter. Slide sideways in Excel. Go even farther so we can see there it is. So we've made it landscape. but you can see these things now. Your merit level conclusion. I have one drafted here. You know what? Most merit level things, we have a page layout that's a portrait layout, to be honest with you. So when you have a portrait layout, sometimes you have to move things a little bit closer. So I'm just moving some stuff around. So that little dotted line is my page break. So here's my calculated bits, which usually live right underneath the graph, and here's my conclusion. Okay? So let me just check the edge of this page. Sure enough, I need to pull this graph in so that it doesn't pull that text box in so it doesn't overlap page, pull this text box in so it doesn't overlap page, and pull it down so I'm not missing any text.